Okay, in this video we're going to go through one more modification of a cubic equation of state. Recall that for van der Waals, we have a critical compressibility factor that equals 3/8. This is better than ideal gas for real materials, but still not great. And so over time, there have been a number of modifications. And we talked about this earlier in our explanation and discussion of the general cubic equations of state. So the modifications have to do with the capturing more information and material about the materials. So it gets it can get insanely more complicated. Even for simple materials like water. Water needs greater than 50 parameters to even be reasonable, and it's not even great to approximate the behavior of water. One of the common things that was found that's useful is to account for differences in materials. And calculating vapor-liquid equilibrium calculations, what these curves look like, to account for differences. There's a variable, measurable quantity, just a parameter, called the acentric factor. Now, what is the acentric factor? This is not the eccentric factor, but it maybe has something to do with being somewhat eccentric. It's always given the symbol, the symbol omega, little omega. And what this is equal to is minus 1.0 minus log base 10 of the vapor pressure at a reduced temperature of 0.7, all divided by the critical pressure. This is a parameter that's been found. If you measure this one value of what this is, this vapor pressure is, at a reduced temperature of 0.7, which means you're in the regime where you're less than 1, which means you can have more than one phase. And what this is the acentric factor. It's like a bridge between microscopic and macroscopic properties. Microscopic and macroscopic properties of a material. So this can account for more nonlinearities in the 1-to-1 and 1-to-2 and whatever other kind of bonds is considered there. It has to do with the molecular structure. Is it spherical, or is it rod-like, with dipoles and moments and things like that? So that's a useful term, and it's used a lot in the equation of state that is pretty heavily used. It's called the Peng-Robinson equation of state. And it's a cubic equation of state, and the equation for the Peng-Robinson equation of state is RT over V underbar minus B, just like what we've seen before, minus A as a function of temperature, all divided by V underbar times V underbar plus B times V underbar minus B. Now we just have to make substitutions in for A and for B. Okay? So A is a function of temperature. And this has been shown to have this value, 0.45724 r squared Tc squared over Pc times alpha of temperature. But what's alpha? Well, let's do B first. B of temperature equals 0.07780 RTC over PC. Alpha, well, let's just do it for square root of alpha, is equal to 1 plus kappa times 1 minus the square root of T over Tc, close parentheses. But we have to know what kappa is. So kappa is equal to 0.37464 plus 1.542226 omega minus 0.2692 omega squared. And omega is the acentric factor we just described. So this is the equation set that you will be using for some vapor-liquid equilibrium computing calculations. There's nothing you can do with this analytically, so there's no point of even trying. That's why we're going to use a computer to do so. And the steps that follow explain to you exactly how to do this.